Hi, this is Mrs. Barbara. This is Physics Chapter 13, Modern Physics, Video 2. Today's topic is continue with wave-particle duality of energy and matter, Part 2. The objectives are know wave has particle nature and matter has wave nature. Understand the meaning of wave-particle duality of all matter and wave. Be able to determine the energy of a photon based on its frequency or wavelength. Be able to determine a photon's type using the EM spectrum chart. Be able to use or interpret a graph of photons' energy versus frequency or energy versus wavelength. Let's take a look at this video.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Okay, so matter have both particles and wave nature. So just as EM radiation has both wave and particle characteristics, matter in motion has wave as well as particle characteristics. The wavelength of waves associated with motion of ordinary object is lambda equals h over p. This is derived from p equals h over lambda. For example, if let's figure out the wavelength of a baseball that's moving about 100 miles per hour. By using this equation, lambda equals h divided by mv, we'll have lambda equals 1.02 times 10 to the negative 34 meters. This is a very, very small number. In fact, it is smaller than the size of a regular nucleus. So it is obviously not detectable. However, the wave nature, such as diffraction and interference patterns of particle can be observed if the particles are very small, such as electrons. So as you can see in the video, that is the electron diffraction called the double slit experiment. So in summary, wave has particle nature. It has momentum just like a particle. The particle also has wave nature. Its wavelength, lambda equals h over p. Okay, the example is what is the energy of a photon with a wavelength of 4.5 times 10 to negative 7 meters? What type of photon is it? To find energy, we use this equation equals to hc over lambda. You plug everything in, you should have 4.42 times 10 to the negative 19 joules. Straightforward. What type of photon is it? Check your reference table, and it looks like 4.5 times 10 to the negative 7 meters. Could be three possibilities. It could be ultraviolet, visible light, or infrared. So in order to find exactly, we have to find its frequency. Frequency equals c over lambda, so that gives us 2 times 10 to the 14 hertz. Well, from reference table, 2 times 10 to the 14 hertz actually is the infrared light. Another example, a photon of which electromagnetic radiation has the most energy. So we know E equals to H times F. Whichever one has the highest frequency has the highest energy. So out of all this, X-ray has the highest frequency. So that is the one has most energy. Another example, which phenomenon best supports the theory that matter has a wave nature? So the only thing we can see the wave nature is very small particles, which is electron. Photon is not matter, right? So only electron momentum or electron diffraction. Well, diffraction is a wave nature, so the answer is electron diffraction. Another example, as the wavelength of a photon increases, what happens to its momentum? Well, momentum is inversely related to wavelength. So as wavelength increases, momentum decreases. That's it for today. Thanks for watching.